Hello, all. Welcome to yet another episode on petroleum refining. So far, we have seen several aspects of petroleum refining, starting with the raw materials, the basic petroleum chemistry, the nature of crude oil and natural gas, the primary processing and secondary processing, that is the manufacturing of petroleum products, and even the maintenance aspect of different equipments. But today we are going to see yet another important aspect known as process control and automation. What are we going to see in this episode? We are going to talk about basics on measurements, why instrumentation and process control, specifically for refining, basic measurements and process plants, and we are going to talk about DCS system and SCADA system, and finally the plant information system and how the process data flows from the field room to the boardroom level. Let's start with the basic concept known as measurement. Measurement is the assignment of numbers to objects or events. For example, we measure length in centimeters, millimeters, meters, or kilometers. We measure weight of an object in kilograms or pounds, or we measure the temperature in degrees centigrade or in Fahrenheit. Measurement is a cornerstone. Most natural sciences, technology, economics, and quantitative research in other social sciences. Any measurement can be judged by the following meta measurement criteria values: level of measurements, which include magnitude, dimensions, and uncertainty. Coming to process plant, specifically petroleum refining, why instrumentation control and process control is very important. So, it is to primarily safeguard the plant and personnel. Without knowing the operating parameters, the safety of the plant cannot be ensured. And also to run the plant in a steady state manner, that is, to run the plant in the design conditions. So, if it is deviating from the designated plant parameters, then only with the instruments and process control we will be able to know that. Then to finally to produce on spec materials, that is market sellable materials. Without proper instrumentation, you will be able to run the refinery, but there is no guarantee that you will be able to produce on spec material, that is the market sellable material. What are the units of measurement in the process plants? There are four basic units that are very vital in any process plants, including petroleum refining. That is temperature, flow, level, and pressure. These are the basic measurement parameters in any process plants. Assume that there are 1000 instruments, almost 90% of the instruments will be measuring any one of these parameters like flow, temperature, pressure, and level. There are some more parameters that are being measured in a continuous fashion with the help of instruments. So, for example, it can be a density, online density monitoring, or air emission analyzer, or moisture analyzer in your product. So, these are all slightly special instruments, while the previous instruments to measure the parameters known as flow, temperature, pressure, level, they are all very generic in nature. So, in any process plant, lot of complexity would be there. There will be multiple parameters that will be critical in deciding the product flow as well as the product quality. Definitely, the process parameters need to be monitored. For example, this is a boiler feed water drum, and the water is coming from an upstream unit in a continuous fashion. And in this particular drum, the heating steam is admitted, and finally the dissolved gases are vented out, and finally the water which is free of gases, they are pumped to the boiler. So this is a continuous process. As long as it reaches steady state, you need not have to bother about measuring the process parameters. But obviously there will be a lot of disturbances and external variations wherein the process parameters need to be continuously monitored with the help of instruments. Now if you see here, there are a lot of instruments put into the same system. For example, the treated water flow is primarily the function of a level controller in the boiler feed water drum. So, if the boiler feed water drum level is dropping, then the control valve will open and it will admit more amount of the water into the drum. The pressure in the drum is regulated by the flow of the steam. So, you can see the instrument regulating the flow of the steam. There are three control valves and three different instruments. One is the flow instrument, which is regulating the water going to the boiler, and then a level instrument, level controller is regulating the flow of the water, and the pressure of the drum is controlled by the flow of the steam. So, this is how the process parameters are monitored as well as regulated, and this is one of the simple examples. Now, let us try to understand what is known as open loop and closed loop in instrumentation. So, in the top picture, there is a pump, and the pump is pumping from upstream to the downstream in a continuous fashion, and the flow is monitored, and the process parameter, which is known as process variable PV, it is going to the control room. So, assume that there is a disturbance in the upstream unit or downstream unit, and obviously there will be change in the flow. So, assume the control room operator is monitoring this variation in the process flow and is asking the field operator to regulate the valve to maintain the flow, then it is known as open loop. Here the measurement is only coming in a one-way direction to the control room, and which is conveyed manually to the field operator. Now, let us see the second scenario where a little more complexity is added. Here also you have a flow sensor, and it is measuring the flow of the stream, and the process variable is not directly going to the control room. It goes through a process controller and finally reaches the control room operator. A process controller is nothing but a microprocessor, and the microprocessor also receives the another input from the control room operator known as set variable or SV. The microprocessor continuously monitors the process variable and set variable, and based on the difference between these two values, it is sending the output or OP to the control valve. And if at all any disturbance is there between process value and set variable, then accordingly the output will be varying, and accordingly the flow will be regulated and adjusted. Here in this case, the process variable comes from the field to the control room, and the set variable comes from the control room to the microprocessor, and finally the output goes to the control valve. So, this is why it is known as a closed loop, whereas in the previous case it is just one-way traffic, and it is known as open loop. So, it can also the first scenario can be called as just an indicator, whereas the second scenario is an example for the controller. So, in a petroleum refinery, so many process parameters need to be monitored, and as I said earlier, pressure, flow, level, temperature, and for all that different kinds of instruments will be deployed. And as a field operator, it is his job to note down all this reading at a set periodicity. For example, once in 2 hours or once an hour, he has to take a logbook and note down all these readings to ensure that the plant is not upset and the plant is running in steady state condition. And this is how so many instruments will be there. So again, when I meant instrument, it will have a lot of subcomponents, starting with the sensing element, microprocessor, final control element, and a current to pneumatic converter. So it will include, the loop will include several small components inside the instrumentation loop. A long time back, that is 3 to 4 decades back, before the advent of computerized process control system, most of the continuous process units used to have an analog control room. In an analog control room, all the instrument readings will be displayed in the control room, again with another set of the user interface. For example, with the help of a dial gauge, we will be able to see the level in the boiler drum. With the help of a recorder chart, you will be able to see the trend of a critical parameters like reactor temperature, etc. For every instrument in the field, there will be a corresponding indicating instrument in the control room. And again, the control room operator used to jot down all these control room parameters in his own logbook every 1 hour or every 2 hours. And a few decades back, the computers have started playing a huge role in the process control system, and that is where the distributor control system started coming into employed in the continuous process industry, including petroleum refining. Distributed control system, or in short known as DCS, is a computerized control system used to automate the processes in various industries, including petroleum refineries. In DCS, the control elements are not only located in the central location but are also distributed throughout the system, with each component subsystem controlled by one or more controllers. So the intelligence is distributed across the section of the plant. So let us see in detail about the different features of distributed control system. The entire system of controllers is connected by networks for communication and monitoring. DCS comprises of distributed microprocessors, networks, and monitors, etc. And in this picture, you will be able to see the different aspects of the operator interface in a control room, DCS control room. So, for example, here we have multiple monitors to show the different viewpoint of the process control plant. For example, one screen is showing the process flow diagram, the other screen is showing the real-time trend, and other screen may be showing the alarm summary, etc. By scanning through the different monitors, the control room operator will be able to figure out whether the plant is working in a steady state manner or if some parameter is deviating from the normal. So accordingly, he will be alerting the field control room, or from the control room certain actions will be taken care. If you see this picture, you will be able to distinguish between the previous picture. So this is a modern control room. In a modern control room, you have giant monitors which will be able to give you a complete overview of even a complex plant. Otherwise, in the traditional control room, you have to go through different screens to understand the process flow, while the modern control rooms give a holistic picture of the entire process plant. So not only that, the modern control room also gives a provision to integrate with the external parameters like the weather conditions. So they are all displayed in a dedicated screen. So these are all some of the important features of the modern control room. Now let's try to understand the different features of the DCS system. So this is the very first feature known as a graphics page. So for every process plant, we have something known as process flow diagram. By going through the process flow diagram from left to right, any engineer, specifically chemical engineer or process engineer, will be able to understand the process, that is how the raw material is converted into products by taking the raw material into different stages, as well the operating parameters in different stages. So in the same manner, in the graphics page, the control room operator will be able to clearly understand the process flow, and a lot of color codes are employed. For example, the instrument are displayed with a specific color. The main process stream, they are mentioned with a specific color. The auxiliary system, they have a different color code. So by seeing these color codes, the process flow symbols, which are known as a P&ID symbol, process and instrumentation diagram symbols, so you will be able to get a complete insight about the process plant. So this is a vital aspect of a distributed control system. The second feature is the trend page or the real-time trend page. Many a times the real-time trend page will be able to show you 8 different parameters at a given point of time. So by seeing this particular page, the operator will be able to see whether the process parameter, any of the process parameter is taking a deviation or a detour. So if all the lines are straight line and within the design conditions, then the control room operator will assume the plant is running smooth. Here there are additional features available, that is, the operator will be able to move the cursor from left to right to understand the parameters at a different point of time, and he will be able to see what are all the disturbance that has happened couple of hours back and what are the current parameters, and even if he wants, he will be able to switch off any of the other parameters. For example, in this particular page, as I said, 8 different parameters like 2 flow indicators, 1 level flow controller, 1 level indicator, 1 temperature controller, like that 8 different parameters are shown. But if at all, if the operator is not able to distinguish between any of these parameters, he can switch off some of the parameters so that he will be able to clearly see the parameters, and he also has got the magnifying feature in the trend page. Then yet another feature of the distributor control system is the alarm summary. So every instrument has got a specific unique ID, and these unique IDs are also provided with the normal operating conditions and the alarm limits. So the alarm limits are generally configured before commissioning of the plant, but at the same time the alarm limits can also be altered while running the plant with the permission from the appropriate authority. So, if at all, if during the startup and shutdown you don't want many alarms, you will be able to modify the alarm parameters. Otherwise, the alarms parameters are set once for all. And after definition of the alarm values set in, then if at all if there is any variation, then the alarm will be coming here, and this will be displayed in a chronological fashion. And by going through the summary of the alarm page, the control room operator will be able to figure out which alarm came in first and which are all the cascading alarms. This way, he will be able to figure out what alarm has caused the problem, what is the root cause for the upset in the plant. Like the distributor control system, yet another terminology is widely used in process control plant known as SCADA. SCADA is an acronym for Supervisory Control and Data Acquisition. It is a system operating with the coded signals over communication channels so as to provide control of remote equipment using typically one communication channel per remote station. The supervisory system may be combined with a data acquisition system by adding the use of coded signal over communication channels to acquire information about the status of the remote equipment for display or for recording functions. So earlier, there used to be clear difference between a SCADA system and distributed control system, and the SCADA systems were generally used for small plants or a specific area where repetitive actions are happening. For example, a gantry operating system or a LPG bottling plant, these kind of plants, while the distributed control system is primarily used for large chemical complex like a refinery or a fertilizer plant. But today, there is a little difference between a SCADA system and a DCS system. Most of the SCADA manufacturers have got into DCS system, and most of the DCS manufacturers have got into the field of a SCADA system. There is not much variation between a SCADA system and a DCS system, and most of the features are available for both the systems. There are specific set of systems on top of your DCS systems known as safety instrumented systems. So generally these are all add-on systems on top of the traditional process control instrumentation. So these are primarily divided into PLCs and ESDs. What is PLC? PLC stands for Programmable Logic Controllers, and ESD stands for Emergency Shutdown Devices. Programmable logic controller is a digital computer used for automation of typically industrial electromechanical processes. PLCs are designed for multiple analog and digital inputs and output arrangements, extended temperature ranges, immunity to electrical noises, and a resistance to vibration and impact. A PLC is an example of a hard real-time system since output results must be produced in response to the input condition within a limited time. Let me elaborate a little more on PLCs. While the distributor control system measures the pressure of the compressor system, the flow of the compressor discharge, the level in the knockout drum, and the flow of the compressed gas, etc., the programmable logic controllers primarily take care of the safe operation of the compressor. For example, whenever the level in the knockout drum exceeds, then immediately an alarm will be generated, and once the alarm is not taken care and if further alarms are triggered, then the programmable logic controller is going to safely shut down the compressor. Otherwise, the process control parameters will get deviated and the entire plant will be upset, which can result into safety incident. So in order to protect the equipment as well the plant as well the operating personnel, PLC will trigger a mechanism to safely shut down the compressor or a furnace. Emergency shutdown systems also have PLCs, but they are very specifically designed on cause and effect. For example, the compressor knockout drum level goes up, then the liquid will carry along with the compressed gases and which will upset the entire plant in the downstream segment. So based on every cause, there will be multiple effects. So if, for example, if the coil outlet temperature in the furnace is going beyond 370 degrees centigrade, then the crude oil will get coked up in the furnace. It is also going to upset the distillation column. So there are several other effects for a single cause. So based on this cause and effect diagram or a matrix, the emergency shutdown system is going to trigger multiple actions. A shutdown valve or a emergency shutdown valve, as known as ESDV, is an actuated valve designed to stop the flow of a hazardous flow or external hydrocarbons upon the detection of a dangerous event. For example, furnace coil outlet temperature going beyond alarm limit is a dangerous event. The knockout drum level going beyond designated alarm limits is a dangerous event. This provides protection against possible harm to people, equipment, or the environment. Shutdown valves form part of a safety instrumented system. Emergency shutdown valves are required by law on any equipment placed on an offshore drilling rig to prevent catastrophic events that has happened in the Gulf of Mexico in 2010. When we talk about safety, it is not limited to upstream, midstream, or downstream. Even in a refinery, the process parameters, the temperature goes up to 700 degrees and beyond in a fluid catalytic cracking unit, and the pressure goes more than 100 atmosphere in a hydrocracking unit, and definitely emergency shutdown systems are mandatory in a refinery. When we talk about process control instrumentation, it is also essential to know the important vendors who are offering such systems. Some of the plant automation vendors who are in this field for several decades are Honeywell, Yokogawa, Rockwell Automation, Invensys, ABB, Emerson, Schneider, etc. So generally it is believed that the process parameters are essential for control room operators for the safe operation of the unit. Yes, agreed. But the process parameters are also essential for certain other stakeholders like the process engineers or the engineers working in the optimization department or the planners and schedulers. Only based on the crude throughput in the refinery as well as the production make, the production engineer will be able to come out with the planning and scheduling for next 6 months or 3 months or monthly planning and scheduling. Similarly, the process engineer, they also need to know about the flow, temperature, pressure, etc., because their job is to safeguard the equipments in the long run. Generally, these other stakeholders who are not control room operators used to visit the control room and they take down the process parameter readings, and then they go back to their respective department, get involved into their core activities. This is a cumbersome activity. They have to collect so many details. So in order to address this system, There are certain companies who are offering now the process historian or real time database. A process historian is a system that sits on top of the DCS system and which will help the process parameters to get disseminated to different stakeholders. It is a database software application that logs or historizes time based process data. Historian software is used to record trends and historical information about industrial process for future reference. It captures plant management information about production status, performance monitoring, quality assurance, tracking, and genealogy and product delivery with the enhanced data capture, data compression, and data presentation capabilities. For example, the process engineer wants to know on a Monday morning what has happened in the particular reactor temperature in the last 48 hours. He will be able to go through the process historian and able to figure out how the temperature has undergone different variations in the last 48 hours. And again, there are several vendors who are very popular in this space. Companies are OSA Soft, they have a product known as Pi System. Then there is a company known as Aspen Tech whose product is IP21. And even the plant automation vendors like Honeywell, Yokogawa, they have their own process historian. For example, Honeywell has got a historian known as Process History Database or PHD, or Yokogawa has got their product known as Quantum PIMS. So this is how the data flows from the field room to the different system. So on your extreme left, you are able to see the different instruments starting with the control room valves, the sensing elements, etc. Then we have the third party tools like mobile devices or laboratory information system, which can also pump in the data to the server, and from the process plant server, then the data is disseminated to the different stakeholders. This is the schematic overview of a historian or real-time database. This is yet another depiction of how the process data is flowing from the field room to the boardroom level. For example, this is known as ISA 95 architecture. ISA stands for Instrumental Society of America. So here in level 1, the field instruments capture the data, and in the level 2, we have the PLCs, DCS systems, and human machine interface, SCADA, etc., which are collecting the data and putting it into a convenient place where data can be viewed under one single interface. Then in level 3, we have the other set of parameters like laboratory information systems, manufacturing execution systems. All these collect the data, and level 4, the data comes from ERP and other business applications. And finally, on top of all this architecture, you will have real-time dashboard which will disseminate the key process information to the decision makers like the operations manager or the general manager operations, who can also monitor the entire plant from a remote location. So in this module on process control automation, we have seen the basics of measurement and why measurements are important for process control, and the basic measurements are happening in process control plants, and we also went through the different features of DCS and SCADA system, and finally how the data is flowing from the control room to the different stakeholders using the real-time historian, and the data flow we have seen with the help of ISA 95 architecture. So this is how we are concluding today's session on process control automation. Thank you so much.